This video is about delta V. So I have three motion diagrams here. The top one is a motion diagram for uniform velocity. The middle one is for velocity increasing towards the right. And the bottom one is for velocity increasing towards the left. So taking them in order, uniform velocity, the motion diagram would look like this. And what you would see is you would see equal displacements and equal time intervals. And so if you had 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, you'd have the same displacement from 1 second to the next second. And underneath this, I've sketched the velocity vectors, which are going to represent this this vector right here represents a velocity vector at 0 time 0, this at time 1, this at time 2, this at time 3, this at time 4, and then there's one at time 5 as well, which I haven't sketched in this case. And the important idea is that there is no change in velocity, so the delta velocity is 0 meters per second. Delta means change in. That means that the acceleration is 0. No change in acceleration. Delta V is 0. Constant uniform velocity. Okay, next case, velocity increasing towards the right. And so the motion diagram is going to look like as you see here. And the displacement from one time to the next time interval is increasing uniformly. And so I've got from 4 little increments here to 5 to 6 to 7 to 8. And that would correspond to the velocity at each one of these times, instantaneous velocity getting bigger by some amount. These are arbitrary velocity units, and so I've just sketched this in. So the velocity here is 1 unit to the right, this is 2 units to the right, this is 3 units to the right. And so this is different than that. Here the velocity is increasing. The delta V is 1 unit to the right. In other words, to get this velocity unit, I'd take the previous one and add this guy to that guy to get that guy. And then I add this guy to that guy to get that guy. And I add this guy to that guy to get that guy. And so the delta V is to the right. And that means the acceleration is bigger than 0 meters per second squared, with the understanding that to the right is positive. That corresponds with a positive acceleration. Okay, last case is the most complicated, and that is where the velocity is increasing towards the left. And let's add a label there because that is important. So V is increasing towards the left. All right, so I start here and I have a displacement from 0 to 1 that's 4 units, and then from 1 to 2 that's 3 units, and then from 2 to 3 that's 2 units, 3 to 4 that's 1 unit. There is no displacement from 4 to 5. Then from 5 to 6 it's 1 unit to the left now, so I've changed direction. 6 to 7, 2 units to the left. 7 to 8, 3 units to the left, and 8 to 9, 4 units to the left. And so again, I've drawn the velocity vectors here, and these are arbitrary. So what I want to communicate here is I'm going from 4 units to the left, to the right, excuse me, to 3 units to the right, to 1 unit to the right. And so the same idea is I've got a delta V here, where in order to get the velocity in the next time interval, I always add this to the velocity of the previous time interval. So delta V plus this is equal to that. Delta V plus this is equal to that. So the delta V is that way, while our interpretation with this positive direction is that would be a negative delta V, which would correspond to a negative acceleration. And so the very important idea here, and we're going to be using this all the time in this chapter and later when we do Newton's laws, is that when you have a delta V pointing to the right, you have an acceleration pointing to the right. When you have a delta V pointing to the left, you have an acceleration pointing to the left. And we'll typically bookkeep this is a plus sign and this is a minus sign.